Hi, my name is Andy Ravenna and I'm a technical trainer for SAS Institute. Have you ever wondered what an ANOVA was or how to read an ANOVA table? Well, that's exactly what I'd like to talk to you about today. ANOVA, which stands for Analysis of Variance, is for comparing the averages or means of two or more populations. A good example of that would be, let's suppose we want to compare the weights of cereal boxes that are produced at two separate manufacturing plants. You wouldn't want to feel cheated by buying a cereal box that wasn't as filled as the next one, would you? So let's suppose we want to do this. I want to compare the weights of cereal boxes that are made at two different facilities. Let's think about this for just a minute. Let's say I take a random sample of 100 cereal boxes from the first plant and I calculate the average. Then I take a random sample of 100 cereal boxes from the second plant and I calculate that average. Do you think those two averages would be exactly the same? Of course not. We expect that they would be slightly different. But here is where the really interesting question comes in. How different do they have to be before I really believe they really are different? In other words, are the differences that we see due to chance alone? To keep things simple today, I'm only going to discuss what's called a one-way ANOVA with two populations. The one-way refers to having only one explanatory or predictor variable. If I use our cereal analogy, our independent or predictor variable is categorical with two levels, the two different manufacturing plants. We could just say plant A and plant B. Our dependent or target variable is continuous. In this case, the weight of the cereal. Now this brings me to the hypothesis of the ANOVA. The null hypothesis is that all means are equal, or there exists no differences between the two weight averages. The alternative hypothesis is at least one mean is different. In the case of the cereal boxes, the two average weights are not equal. So the objective of performing the ANOVA is to determine if the differences that we see are significant. In other words, is the difference more than what we would expect to see by chance alone? When we perform the ANOVA, we will get a p-value. And if that p-value is very low, we will have collected enough evidence to reject that null hypothesis or conclude that the two averages are different. Remember, the p-value measures the probability of observing a value as extreme or more extreme than the one observed if the null hypothesis is true. Let's dig a little deeper into ANOVA by examining some slides that I created. So here's the question we're trying to answer. When are two groups really different? You can see in my example here, I've got measurements from two different groups, Group A and Group B. We could call this manufacturing plant A and manufacturing plant B, and we could assume these measurements are our cereal weights. So you can see in this particular example, I've got three measurements from Group A and three measurements from Group B. And if we were to look at those averages, they look almost exactly the same. Perhaps I would come in and it might look a little bit like this situation where the two averages are starting to look a little bit different, whereas it looks like the measurements from Group B might be slightly higher than the measurements from Group A. Or if we had this situation, it looks like these are coming from two entirely different populations. So we're seeing a very big difference between the groups. And that's really the question we want to answer. When are we just seeing differences by chance alone versus when there's actually a difference between the two groups? This is why we want to perform the ANOVA, or the Analysis of Variance. One of the things that's kind of interesting about the word analysis is that if you go back to its origins, it actually means a breaking up or a partitioning of something into smaller parts in order to better understand it. And that's exactly what we're doing when we're performing an analysis of variance. We are breaking up the variability or partitioning the variability. And when we examine what we've done, we're hoping to get a better understanding. In other words, we want to be able to use this partitioning of the variability to help us understand if a difference in the two population means actually exists. What does this start to look like? Well, if we were to look at the total variability, that would be the total sum of squares, and it's a measurement of that overall variability in our response variable. We can actually take that total variability and we can break it up into two different pieces: the variability between the groups and the variability within the groups. The variability between the groups is actually called the model sum of squares. And as it turns out, that's the variability that is explained by our end variable. Now, the error sum of squares, which is the variability within the groups, that's actually the variability that is not explained by the model. And one of the things that's kind of interesting about this is that if there is really no difference between our group means, then the group means should differ from each other about as much as the individual observations differ from each other. We'll see what that looks like in just a second. So what is it that we want to do? We want to examine this group variability or group variation. And you see I've got some different measurements here, and I've got some measurements from group A, and then the green line here actually represents the average of group A. And then I've got measurements from group B, and here is the average of group B. And then this black line down the middle, that's the overall average of all the data combined together. And that's going to allow us to take a look at the variability within the groups. So when we want to look at the variability within a group, we would compare those individual observations against that group average. Remember, that's called the error sum of squares. We would do this for both groups, all right? That would give us our within group variation or variability. And what we want to do is we want to compare that against the variability that is between the groups. Now remember, that's called the model sum of squares. And the way that we examine that is by comparing the group averages against the overall mean. So what is that going to look like? Let's actually do this calculation for this one example that I have here. So I've taken 6 measurements, 3 from group A and 3 from group B, and these are the actual numbers right here. So the first thing I'm going to do is I want to find out what that overall average of all of the data is. And if we were to figure that out for this particular example, it turns out that that overall average is 6. So here are my 6 measurements: a 3, a 4, and a 5 for group A, and a 7, an 8, and a 9 for group B. All right, so I've got my overall mean. I now know what that is, and we can start to move forward in our calculation of our sum of squares. The first thing that we're going to calculate is the total sum of squares. Where's that number going to come from? Well, what we're going to do is we're going to take each individual observation and we're going to subtract off the group mean, and then we're going to square that value. Now you might ask yourself the question, why are we squaring the value? And it's because if you take all of these differences from the average and you add them up, you get 0. So the only way we can get a measure of the variability is by squaring those values. So I'm going to say 3 minus 6, and then I'm going to square that value. I'm going to say 4 minus 6 and square that value. I'm going to do that for the last term in group A and square that value. Now don't forget, we also have group B. So I want to take each individual item or each individual observation from group B, and we want to subtract off the overall average and square that. Now, when we do that for all 6 of our observations, that gives us our total sum of squares, and it turns out for this particular example, its totals to 28. Now we're going to start to have fun because we're going to plug these values into our ANOVA table. So you could read the ANOVA table. So the first thing I'm going to do is I'm going to plug in my total sum of squares. Associated with that is n minus 1 degrees of freedom, where n is the total number of observations. Now, in my example, I had a total of 6 observations. I'm going to subtract 1. 6 minus 1 is 5. So I'm now going to plug 5 in there. And remember, we calculated the total sum of squares to be 28 for our data. All right, great. Let's keep on filling out this ANOVA table. I'm going to move up to this error line next, and we're going to calculate the error sum of squares. Remember, the error sum of squares is the variability that is not explained by the independent variable, and it is what we call the within treatment variability. How am I going to calculate that? Well, first I need to find the group average for the first group. And so the average of my group A data turns out to be 4. Then what I'm going to do is within this group, I'm going to subtract each individual point from the group average and square that value. So we're going to get a 5 minus 4 and square that. We're going to get a 3 minus a 4 and square that. And we even get a 4 minus 4 and square that. So that's the within treatment variability for group A. But we're not done yet because we need to do the same thing for group B. So the overall average for group B is 8. And we want to take each individual term in group B and subtract the group average and square that. So we're going to do that for all 3 of my measurements in group B. When we do that for both groups and we add all that up, we get an error sum of squares of 4. I'm going to continue to fill in my ANOVA table. So here is my error sum of squares, and it has associated with it n minus k degrees of freedom, where n, remember, is the total number of observations, and k is the number of groups. So here I have 6 observations. I have 2 groups, group A and group B. So 6 minus 2 is 4. We start to plug in the degrees of freedom. We have 4, and it also turns out that our error sum of squares is also 4. All right, let's move up to the final line, the model line. So now I want to calculate the model sum of squares. This is the variability that is explained by the independent variable, or what we think of as the between treatment sum of squares. And the way that I'm going to get that is I'm going to compare the 2 group averages against the overall average. So the first thing I'm going to do is I'm going to take my first group average, which is 4. I'm going to subtract off the overall average, which is 6. We're going to square that value. And then remember, for group A, we had a total of 3 measurements. So we're going to multiply that squared difference by 3. And then, of course, we need to do that for group B. So the group B average is 8. We're going to subtract off the overall average, which is 6. We're going to square that value, and we're going to multiply that by 3 because there were also 3 measurements from group B. When I total all that together, I get my model sum of squares, which is 24. Here's where the model sum of squares goes in. It actually has k minus 1 degrees of freedom associated with it, where k is the number of groups. So remember, we have 2 groups minus 1, which means we're going to have 1 degree of freedom. And remember, my calculated model sum of squares was 24. Now, one of the interesting things that you might notice at this point with my ANOVA table is that if I add the model degrees of freedom with the error degrees of freedom, I get the total degrees of freedom. And the same thing happens with my model sum of squares and my error sum of squares. They're actually going to add together to be the total sum of squares. All right, we're not done with the ANOVA table quite yet. The next thing I want to calculate is the mean square of the model sum of squares. Now that is very simply the model sum of squares divided by its degrees of freedom. So 24 divided by 1 is the mean square of my model. I want to do the exact same thing in order to calculate the mean square of the error sum of squares. We're going to take the error sum of squares and divide by the degrees of freedom. So in that case, it's going to be 4 divided by 4 is 1. So when I start to fill in that portion of the table, I now have the mean square for the model and the mean square for the error. And now we're finally beginning to see what's going to show us whether we have a difference or not. We're going to calculate the F value. The F value, as it turns out, is that ratio between the mean square of the model and the mean square of the error. And here's the theory. The theory is that if the null hypothesis of all means being equal is true, then the expected value of those two mean squares is going to be approximately equal. Or if those two things are equal and we take their ratio, then the F ratio will be approximately 1. Well, here, when we take 24 and we divide by 1, you can see that we get a very large F value. And if we look up the P value from the F distribution and the appropriate degrees of freedom, we're going to see that we have a very small p-value. And you may remember from your last statistics course, if the p is low, the null must go. So in this case, we've collected enough evidence to reject our null hypothesis that all the means are equal. Another way of thinking about that is that we've gathered enough evidence now to see that it looks like there's a difference between our two group means. Well, guess what? You now know where all of the numbers come from to fill out that ANOVA table and what they mean. So the last thing that I want to do with you today is I'd like to move into SAS Software and show you how you can actually calculate an ANOVA table. So I've logged into SAS Viya for Learners, and I've moved into SAS Studio, and I've started up a brand new program. Now, if you would like to follow along, you could do exactly the same. So you could just log in and you could type in the code that I just finished typing in. So you can see what I've done here is I've created a data set called work.serial, and I'm going to duplicate the exact same numbers that I just showed you in my example. So I'm going to input two variables. I'm going to use the group and the weight, and we'll use a data line statement so we can type the data directly into this data step. And so you can see here are my 6 measurements. There's 3 measurements for group A and 3 measurements for group B. Then we're going to finish off the data step with a run semicolon, and I'll do a proc print. Let's go ahead and run that and just verify for ourselves that we actually have the 6 values that we want. 3 numbers or 3 weights for group A and 3 weights for group B. Great. Now I've got my data table, and now I'd like to perform an ANOVA. And doing this in SAS Studio is very easy because what I can do is I can use one of those tasks that already has everything available for me. So watch this. I'm going to go under my statistics list. We'll open up the linear models. And here's my friend, the one-way ANOVA. So we're going to start up a one-way ANOVA, and we're going to perform this one-way ANOVA on the data table that I just created. So let's open up. We're going to go into the work library and open up that serial table that I just created. Then we're going to specify the dependent variable, which of course is going to be weight. We're going to try to explain the weight by looking at, and here's my categorical variable, which is going to be group. Remember, we have 2 group levels. A and B. Now, believe it or not, that's all I have to do, because the cool thing about SAS Studio tasks is you will see that while I was pointing and clicking, it actually wrote the code for me, which is very nice. So I'm going to go ahead and click on the Run button, and let's take a look at the results. And hopefully you're not going to be surprised here. So I'm going to close up my task tab so we have a little bit more real estate here, and I'm going to move this over just a little bit and take a look. Here is my analysis of variance table. And hopefully these numbers look familiar to you. So you can see my degrees of freedom are 1 and 4 for a total of 5. The model sum of squares is 24. The error sum of squares is 4. And that means my mean square mean square for the model is going to be 24 divided by 1. My mean square of the error is going to be 4 divided by 4. We look at that ratio, we get an F value, which has a very low P. And so we've basically gathered enough evidence to reject our null hypothesis that all means are equal. So in this case, we only have 2 means, so it means that they look different. And you can actually take a look at this plot that's provided for us, and we can see that it really does look like these 2 sets of weights are coming from different populations, or there's probably some difference between the plants. Okay, great. You know what? Let's try this one more time, but this time I'm going to use some baseball data that's already provided in the SAS Help library. So here's what I'm going to do. I'm going to come back over to my tasks, and I'm going to start up a brand new one-way ANOVA by double-clicking on it. And so now we're going to do a second one-way ANOVA. This time, instead of using the work.serial table, I'm going to open up the SAS Help library. And in the SAS Help library, you will see that there is a baseball data set. And this, of course, has information about some different baseball teams and different divisions and the number of hits they made. And so here's what we're going to try to do. We're going to see if there is a difference in the number of hits between these 2 different divisions. There's an East division and a West division. So my dependent variable in this case is going to be the number of hits. My categorical, or in this case, my explanatory variable, is going to be a variable named division, which has 2 levels to it. And once again, that's all I have to do in order to create an ANOVA using SAS Studio. I'm going to click on the Run button. Let's minimize my SAS tasks. That gives me a little bit more real estate. And let's take a look at the ANOVA table. So let me open this up just a little bit more. Here's my ANOVA table. So now we can see that we've got the model degrees of freedom, the error degrees of freedom for the corrected total degrees of freedom. I can see the sum of squares for the model, the sum of squares for the error. We then remember divide to go all the way across to get the mean square model and the mean square error, which gives me an F ratio of 2. That's not as big as the other way, F that we just saw. And so in this case, the p-value associated with that F, with the correct number of degrees of freedom, is about 0.1397. Well, typically we compare that to a cutoff of 0.05. If it's less than 0.05, we reject the null hypothesis. In this case, that probability of experiencing that difference as differences as large as the one that we see or larger is about 0.1397. That's that probability, which in this case is greater than 5%. So we fail to reject the null hypothesis. What this means is we have not collected enough evidence for there to appear to be a difference between these 2 averages. Now let's look at the plot. I'm going to open up this plot just a little bit more. And you can see here's the distribution of hits between the East Division and the West Division. And when we look at the box plots, they really don't look that different, right? And so in this case, my ANOVA did not detect a difference between these two averages or between these two divisions. I hope you learned something useful during our short time together. You may think I covered everything you would ever want to know about ANOVA, but guess what? I didn't. There's a couple of features I just did not have time to cover. First, I did not talk about what are the assumptions involved with performing an ANOVA. And second, I did not talk about what happens if you want to compare more than two averages. Well, to learn about that and more, please check out the links below. Please leave me any comments or questions. I promise to get back to you. And if you like what you saw, don't forget to subscribe. I'll see you next time.